In this video, we will discuss a simpler example of finding the epsilon-delta definition of a limit, or excuse me, using the epsilon-delta definition of a limit to show that a given limit has a particular value. And so let's graph this just to make sure we understand what's going on. Let's try to graph it to scale. I'm interested in the limit as x approaches 2 of this particular function. It's just a linear function. And the function is y equals 3x minus 1. So when x is 0, y is -1, and then it has a slope of 3. So we go up, we start here, and then we go up 3 and over 1. Then we go up 3 and over 1 again. So that is our function. And I think it's clear just from looking at it that as x approaches 2, the y values on the graph approach y equals 3 times 2 minus 1, which is 5. It's a continuous function. We can draw the line without picking up our pencil. But as we approach 2 from the left and the right, both limits are the same. They're both equal to 5. But we want to prove that this is true. I'm using the epsilon-delta definition. Let's review what that is. The limit as x approaches c of f of x is equal to L. That equation is equivalent to the following statement. For every epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x minus c, which is less than delta, implies that the absolute value of f of x minus L is less than epsilon. We've already talked about this definition, and this, remember, means for every. And this, remember, means there exists. And this means such that. And this arrow means implies. Okay, so for every epsilon greater than 0, there exists a delta greater than 0 such that this inequality implies this inequality. Or equivalently, x is not equal to c, and x is between c minus delta and c plus delta, implies that f of x is between L minus epsilon and L plus epsilon. So we're saying any epsilon we choose, we can always find a delta, so that this implies this. So let's draw some lines over here to illustrate this concept, and then try to find the relationship between delta and epsilon. So let's choose epsilon to be 0.5 just for our picture. So our limit is 5, and we're going to add and subtract 0.5 from 5 and draw a couple of horizontal lines. This is y equals 5.5 or 5 plus epsilon. We're subtracting 0.5, or excuse me, from 5 as well. This is y equals 5 minus epsilon. So again, this says that the y values on in this interval, or we can always get y values on this interval from here to here if we choose x values on the appropriate interval. And we'll also draw a couple of lines here where our horizontal lines intersect the perpendicular. Gonna be a little bit difficult to see, but we'll do the best we can. This is supposed to be x equals 2 minus delta 1. And this is supposed to be x equals 2 plus delta 1, or excuse me, delta 2. And delta 1 is the distance from here to here. And delta sub 2 is the distance from there to there. Now, because my graph is not to scale, it looks like delta 2 is actually smaller than delta sub 1. But it turns out that they're actually the same in this example because it's a line, but we'll see. We'll see what that is. So let's prove this. Now, the way that we prove this is we choose epsilon to be greater than 0. Excuse me, I think I said choose. We're going to let epsilon be greater than 0. Any epsilon we want just has to be positive. And then we're going to choose delta to be a function of epsilon. And then we will assume this first part. So we will assume that 0 is less than the absolute value of x minus c, which is less than delta. In this case, c is equal to 2. The limit is equal to 5, and this is our f of x. So we'll assume that 0 is less than the absolute value of x minus 2, which is less than delta. That just means that x is not equal to 2, or we're not concerned about what happens at x equals 2 when we're discussing this limit. And the absolute value of x minus 2 is less than delta. Now we want to look at the absolute value of f of x minus L now. And f of x is 3x minus 1. Actually, I feel like I may have already done this. I think we did. The limit is 5. And if we simplify that, we have the absolute value of 3x minus 6. And that has a common factor of 3. So we can factor that out. 3 times x is 3x, and 3 times negative 2 is the negative 6. And we want to compare this to this. We want to find a way to show that this is less than epsilon if x minus 2 is less than delta. Well, since the absolute value of x minus 2 is less than delta, we know that this is less than 3 delta. So if we let delta equal 3 times epsilon, or excuse me, epsilon divided by 3, the 3's reduce, and we have the absolute value of f of x minus L is less than epsilon. Oops, I keep saying 3 epsilon, it's 1/3 epsilon. If you're saying that really didn't help me understand the concept very much, we'll just think about it. This is saying like if we're on the interval from 4.5 to 0.5. Oops, I wrote a 3 instead of an epsilon. Let's say epsilon is 0.5. Then L or y equals L plus or minus epsilon is L equals 5 plus or minus 0.5. So our y values are between 4.5 and 5.5. The question is, what's the corresponding delta? According to our calculations, the delta should be 1/3 of epsilon. Or 1/3 of 1/2, which is 1/6. So what we're saying then is if delta is 1/6, then we're saying that if x is on the interval from 2 minus 1/6 to 2 plus 1/6, then our y values are in this interval. Actually, maybe I should make this table down here. So we had epsilon equals 0.5. Y equals L minus epsilon and y equals L plus epsilon. We've just finished this table. Just to help us understand the concept. For this particular example, the value of delta that worked, where delta is a function of epsilon, is 1/3 of epsilon. And I want to look at x equals c minus delta and x equals c plus delta as well. So this is 5 minus 0.5, which is 4.5. This is 5 plus 0.5, which is 5.5. This is 1/3 times 1/2, which is 1/6. And I've got fractions and decimals, but it's just easier to think about it that way. And this equals 2 minus 1/6. And this is 2 plus 1/6. So again, we're saying that if epsilon is 0.5, so we want our y values in that range. Well, then we just have to go, we start at 2 and then subtract 1/6, then add 1/6. And as long as our x values are within 1/6 of a unit of 2, then the x values in here will map to y values in there. And the same could be done at epsilon equals 0.1. You'd say, well, I want epsilon to be even smaller. Let's let epsilon be even smaller. Well, then the lower limit for y, the L minus epsilon would be 4.9. And the upper boundary for our y values would be 5.1. So we're saying all of our y values on the graph of y equals 3x minus 1 are going to be between 4.9 and 5.1, as long as we're within 1/3 epsilon of c, and this is 1/10. 1/3 of 1/10 is 1/30. So if we are within this interval, where we start at 2 and we subtract 1/30 and we add 1/30, then all the x values in there will map to y values in there. And we can do this for smaller and smaller epsilon. It doesn't matter what epsilon is, even if it's this 0.01. We have 4.09 there, or 5.01 there. And this is 1/100th times 1/3, so we got 1/300. Then our range of x values will go from x equals 2 minus 1/300, x equals 2 plus 1/300. If I want my y values between these two values right here, actually this should be a 9. Sorry. 4.99 and 5.01. So we're getting very, very close to 5 now. Then our epsilon values just need to be within 1/300th of 2. I said epsilon values. Our delta needs to be 1/300, so that our x values are within delta units of 2. So they're in this interval. So this interval gets smaller and smaller as this interval gets smaller. And that's how we do that proof. The calculations are relatively simple. For a line in general, if this is y equals mx plus b, the y values are this factor in the denominator is just going to be 1, or the factor in the denominator, excuse me, is going to be the slope. And you can show that every time. But it gets a little bit more complicated doing the calculations when the function's nonlinear. But we did that in a different example. Let's just do the general case for a line. So let's show that the limit as x approaches c of mx plus b is equal to mc plus b. We'll let epsilon be greater than 0. We're going to choose delta to be some function of epsilon. And then we'll assume that 0 is less than the absolute value of x minus c, which is less than delta. And we know what that means. X is not equal to c, and this absolute value is less than delta, which just means that we're on an interval centered at c, and we subtract delta to get that limit to the left, and we add delta to get that boundary to the right. So we've got that. And then we want to look at the absolute value of f of x minus L. this case, f of x is just mx plus b. The limiting value is mc plus b. Distribute the negative. The b's reduce. And now you've got the absolute value of mx minus mc. And you can factor out the m. You say, well, that absolute value of x minus c is less than delta. So this expression is going to be less than m times delta. So if delta is equal to epsilon divided by m, the m's reduced, and you just get that the absolute value of f of x minus L is less than epsilon. So we're going to require, to get from here to here, that delta be equal to epsilon divided by m, or if you want, you could say that it's less than epsilon for m. It would really not change anything except for that sign. We would just use a less than rather than an equal sign. And I hope you can see why that's the case. If this has a slope of 3, well, the x values have to be in an interval that's, or the corresponding width of the interval has to be 1/3 of that. And that's what this shows right here. So again, the definition says, for every epsilon greater than 0, no matter how small, there's a delta greater than 0, such that if x is not equal to c and x is on this interval, then the y values are on this interval. So we can pick any epsilon we want. We can get as close as we want to y equals L, as long as we choose the x values as close as necessary to x equals c. And this is how close we are to x equals c. The delta represents how close we are to x equals c, and the epsilon represents how close we are to y equals L.